Okay, fine. Now can you see the program? The name of my program is badcnt.c, which I executed initially just to show you the problem of. Can you see this? Okay, no problem. Let me close this. Okay, so this was the program I shown you at the initial stage to show the problem of data inconsistency if shared variable is accessed concurrently. And last time I tried with semaphore, whatever the functions I discussed, like declaration of semaphore variable. So those steps also I mentioned here, but previously it was not working, and the reason was on Mac OS. Okay, uh, these unnamed semaphores have been not implemented as long as these POSIX semaphores are considered. So I just changed one step there. Rather than making use of unnamed semaphore, I converted it to named semaphore, but the steps are still same. Just one change. So step number one, as I mentioned, this is the same thing. Include the header file semaphore.h. Step number two, declare semaphore variable. Now one change I did here, and that is previously was same_t and just log. Excuse me. Now I have pointer variable here. So same_t star log. That is one change. Step number three, I just highlighted it. Initialize the semaphore variable. Previously I used same_init. That is for the unnamed semaphores. But for named semaphores, I use something like same_open. Now I need to give some sort of name. So for example, I just given my lock as a name. This is same thing like opening any file. Meaning of this is o_create. So this is one of the option. So create new semaphore with the name mylock. o_exl makes sure that if already this semaphore is available, then it will result in error. Okay, so exl is exclusive. Next is 0644. These are the permissions. So read write permissions are given for the owner. Just read permission for the group members and read permission for this. And again exactly like the read write execute permissions we set on Linux, right? And last thing is one. That means I want to initialize this semaphore with value 1, where 1 refers to the resource is free. If already a semaphore is available with this name, then it definitely fails. Same_open fails, and that fact is known to us with the value same_filled. So if lock whatever return type same_open, if it is same_filled, it says like display the error, can't create semaphore, and simply terminate the program. Because if we cannot create semaphore, no need to continue with this code. That is the reason I use exit 0. Now this was as usual the previous part, and once you're done with, initially I use same_destroy. Now because I use name semaphore, same_close and same_unlink. So closes the semaphore variable lock, and unlink it removes from your operating system. And then I want to display the what count is that. And in the thread routine count, same thing, same wait and post is used to mark the entry and end of critical section. So wait means acquire lock. Once you acquire lock, go into the critical section, update the shared variable. Once you've done it, stop. That is really the lock. Okay, so with these minor changes, let me open the terminal and now compile this code. Uh, ls-cnt.c. Yes, it is there. Now compile it. Because I'm using threading that -elp thread link p thread library. Now I want to execute it with a value of 1000, and now this time I get up to 1000. Execute it with say 5000. What I expect is 10,000. Execute it. Now you imagine of any value. So 25,000, you'll get 50,000. So this time, because access to said variable CNT, especially here in the critical section, is now synchronized by making use of these semaphores, definitely will get the correct count, right? Is there any doubt in this? Is there any doubt? Anyways, if you are working on Linux platform, Linux still supports Linux still supports same underscore init and same underscore destroy. No need to go with open, close, and link. Okay, so that you can do. Now let me stop this sharing. Fine. Just a minute. Fine. So let's continue to problem solution. This is the most important problems whenever you need to think in terms of simultaneous execution or say concurrency, especially synchronization, and this is required even for your campus interviews also. Okay. So now what I'll do is, hello. Select to solve. Hello. Hello. the classical problems. Three problems we'll be discussing. One is the bounded buffer producer consumer problem. Second one is readers and writers problem. And third one is dining philosophers problem. Three problems I just mentioned in unit number 1, I guess. But now in this, we'll discuss the problem and the solution for that. Right? So let us start with the first one, bounded buffer producer consumer problem. Now, I already mentioned about the producer consumer problem. There are set of processes to produce elements, and these produced elements will be stored in shared data. And few other set of process is like consumers, they consume it from the same share. So it is kind of, I already mentioned, it is like the queue. So for example, let me use annotations here. It is something like this. So we'll assume this is the queue and capacity of this queue is n. That means n elements can be stored. So it is like space for first element, space for second element, space for third element. Similarly, we have total n. So that is the capacity of 1, 2, 3 up to n. So that is the capacity of this buffer. And because this is the limited, that is the name bounded buffer. Okay. Now, can be, for example, element produced will be stored at first location, second produced is at second location, third element will be at third up to n. Once you done with n, suppose for example, consumer has consumed element 1 and 2, then definitely we'll utilize this as the circular queue. So this is kind of circular queue kind of a thing. Okay. Now because this buffer is shared between many processes or say many threads. Okay, just two categories of processes. One is the set of producers who will produce the elements and put them into this buffer, and other set is consumers who will consume, that means they will remove the element from this queue. Right? Now, how we can devise solution making use of semaphore for this? Right? So, the data structures are mentioned here. For example, we have number of buffers n, right? Now, 3 semaphore variables can be utilized in this device solution. One is the mutex, and this we initialize with 1. And meaning of 1 is it is free. Okay, so whoever is waiting on this will be granted the permission because it is not being used by anybody. Now, whenever you are reading or writing from this buffer, we'll utilize this mutex so that we'll make sure that the updation of this buffer will be the critical section. So for that, mutex will be utilized. So definitely, because it is mutex, it will be binary semaphore, where value of 1 means free and value of 0 means busy. The second semaphore is like its name is full. This will be initialized to 0. And third semaphore is empty. This will be initialized with value of n. So kindly note that the semaphore variable full and empty, these both are not binary semaphore, they are counting semaphores, where full will hold out of n buffers, how many buffers are right now used. So for example, suppose 2 tons of producers have executed. So first producer produced the element and put at location 1, second producer produce another element and that is put on second location. Okay, so out of n, first and second are full, right? So the value of this semaphore variable full will be 2 in that case. Okay, so full necessarily indicates how many elements are available in buffer. Whereas semaphore variable empty, which is initialized to n, see the full semaphore variable is initialized with 0. That means initially everything is empty, right? There is not a single element. Whereas semaphore empty is initialized with n, and meaning of this is how many empty locations are there. Like full gives how many locations are occupied. The semaphore variable empty denotes how many locations are available for producers. So definitely initially nothing is produced, so the value of empty will be n. Just you need to make sure that the full plus empty is equal to n. That is as simple as like it. For example, if I have said 10 is the capacity, so that is the value of n, and 3 elements have been produced, so definitely full will have value of 3 and empty will have value of 7. So 3 plus 7 is equal to 10, something like that. Okay. Now given these data structures, we can write the code for producer process as below. So you can check it here. For example, assume that these are the statements which will produce the element. You can imagine something like the random routine which will generate the random number. So whatever the functions you need to call for that, right? So the variable, local variable will be next produced and that will be assigned with some random number. So that is the logic of producing next element. Now the synchronization protocol is important here. Now before adding this newly produced element into the buffer, because that you can imagine like a critical section. Okay, so very first part is, remember, because this is a critical section, this is with wait on mutex and signal on mutex. So acquire lock so that no producers and no consumers will simultaneously put elements or remove element from buffer. So when mutex, signal mutex, they have safeguarded this part. In addition to that, this information is important. Wait on empty and signal on full. Now this is again important. Now what is wait on empty? If there is empty location, at least one, because we have initialized empty with n. Say for example, again, if the capacity of my buffer is 5 and 5 elements are already there, then this producer has to wait, right? So if the value of the empty was 5, then it became 4 for first producer, 3 for second, 2 for third, 1 for fourth, 0 for fifth. And once it becomes 0, sixth producer has to wait. Kindly note that whatever the code is there, pseudocode rather, I can say, in front of you is for producer process. So we need to talk in terms of producers only, right? So that producer, say for example, sixth producer has to wait. Wait for what? Wait for empty location. Getting it, no? So producers has to, there is no space in the buffer, right? And this is somewhat interesting. Why we are writing signal full? Why we are writing signal full? Try to understand signal full doesn't mean buffer is full, right? Signal means because I have produced one element, so I occupied one space of buffer. So definitely I need to signal on number of elements available. Say for example, if initially it was 0, it becomes 1. If initially it was already 3, it becomes 4. So how many elements are there in the buffer? That is what. And that is one thing. And second important thing is, for example, you need to imagine now, suppose there are not a single element available in the buffer and it is turn of consumer. Consumer has to wait for full. Why? Because if there is nothing to consume, consumer has to wait. And how many elements are in the buffer is denoted by the semaphore variable full. So if producer produces it, producer has to increment it. If consumer consumes the element, consumer has to decrement it. And this increment is done by signal operation and decrement is done by wait. Try to understand this, because producers and consumers has to be synchronized, right? They have to be synchronized. So whenever element is consumed by consumer, definitely that creates a space, empty space. That means it will wake up the producer. So if any producer is waiting for empty space, that will be waken up. So both the producers and consumers need to deal with empty and full. And whenever we want to do some sort of modification into the buffer, maybe adding the elements or removing the elements, in that case, that will be safeguarded by mutex, right? So have a look at the consumer process now. So consumer will wait for full. Again, don't get confused because of the name full. Meaning of this is not like consumer will consume only after the buffer is full. No, full is the counting semaphore. Full is counting semaphore, right? If the value of full is 0, that means there is no element. So it has to be. And if it is greater than 0, that means it got the element, right? Again, because we are dealing with buffer here, it will be safeguarded by wait and signal. So wait on full, meaning of that is if there is element to be consumed, otherwise wait, right? Now why signal empty? Because we just consumed one element, right? And because we have consumed one element, that created one empty space. Okay, so signal the empty semaphore. That is the code for producer and that is code for consumer. Any doubt in this? Let me tell you, you are supposed to write programs for this. Maybe using any programming language, doesn't matter. But you are supposed to write program for this producer and consumers. Bounded buffer producer consumer problem. Okay. So 98 participants are there. Do you have any doubt? Please put on chat. And if it is clear, we'll proceed further. Fine. So let us move to the next one. The second problem is reader-writer problem. Now, with reader-writer problem, one more complexity is there, and that is like in producer-consumer. In producer-consumer, whenever you want to update the shared buffer, maybe by producer, maybe by consumer, then in serializable manner access is provided. But that is not with reader writer problem, because reader writer problem is another category of problem where simultaneous reading is possible because we are not doing any update. So again, the among number of concurrent processes, two categories are there. One is the readers and one is the writers. Don't think as like writers are producers and readers are consumers. Because reading can happen simultaneously. So readers will only read the data, they do not perform any updates. And because we are not updating anything, if simultaneously you are reading, that don't create any problem of like inconsistency. Where if it is writer, it can do both. It can read and write. Okay. Now our reader writer problem is allow multiple readers to read at the same time. But if it is turn off writer, writer can like only single writer can write the shared data at the same time. So mutually exclusive access should be given to the writers, whereas we should allow multiple readers. And there are so many variations available for as a solution for reader writer problem. One of such solution is mentioned here, for which the shared data is like one is the data set which you want to read or write. You can imagine this as a even single variable also, or like a array. No problem. Now there is a separate semaphore RW mutex. Now this will be used to synchronize the execution of writers. So this is read write mutex, which will be initialized to 1. That means initially nobody is writing, or nobody is in the writing, we can say. RW is typically for writers, and semaphore mutex will be utilized for accessing the variable this read count. Remember, this read count is not a semaphore variable. This is normal integer variable. But we need to update this, and for which mutex will initialize. So this is initialized to 0. Meaning of this is how many readers are currently reading it. How many readers are currently reading it. So currently nobody is reading, so this count is 0. Now with this shared data, the structure of writer process is given here. This is very simple because we have read write mutex. What we'll do is wait on that. If you actor lock, perform writing operation, once you're done with, signal it. That is release. So here we lock the resource, here we unlock the resource. So lock the resource, update it, unlock the resource. So this is very simple, right? Whereas in reader process, now we need to discuss the solution first of all on logical steps, and then we'll go to this pseudocode. Okay, the solution is very simple. For example, if somebody is already reading, see, if somebody is writing, resource is not available to other writers also, to other readers also. That is what is the mutex. Whereas if somebody is reading, okay, then we can immediately allow other readers, because writer is definitely not there, and for which we utilize the count variable, read count variable. Okay, so see how it works is, for a reader process, wait on mutex because we want to increment the read count. Okay, if I incremented read count, see, I have initialized it with 0. Now I incremented, and if the count is equal to 1, try to understand all 3 conditions. I initialize it with 0. Okay, reader has just incremented it, and if it is equal to 0, definitely this means that this is the first reader. And if this is the first reader, it has to check for RW mutex. Why? Reason is very simple. If this is the first reader, it has to check if writer is already writing there. Okay, if writer is already writing there, we need to check that, because this is the first reader. If this is not first reader, that definitely gives one logical step that nobody is writing it, because first reader already acquired lock on RW mutex. And because this is the binary semaphore, if it is acquired by reader, writers cannot write. Okay, so if this condition is false, for example, if this condition is false, what is meaning? Read count is definitely greater than 1. And if the read count is greater than 1, that means already somebody is reading. If already somebody is reading, signal mutex, because updation of this read count is finished. Now very important thing is wait mutex on read count plus plus. Why signal is not immediately used after updating read count? Reason behind that is if you immediately signal it, what will happen? Read count will be incremented without acquiring RW mutex lock on this. That creates a problem. Imagine something like incremented it, so value of that becomes 1, and suppose signal is used here, and now RW process is there, which will definitely get the lock on mutex because we have signaled it. Read count plus plus, it becomes 2. It will check that read count equal to 2, but previous reader has not acquired lock on RW mutex, so it will directly start reading, which is wrong. Without acquiring lock on RW mutex, you cannot read, because that will conflict with the writer. Okay, so this step is important. It should be signal mutex should be after acquiring lock on the read write mutex. Now this is required only for first reader. If second reader is there, read count is definitely greater than 1, they will immediately start reading. Okay, once you finish reading, now once you finish reading, I want to decrement this read count. Okay, and in order to decrement this, I'll acquire lock on read count, wait mutex, and signal mutex. So this will be the critical section. And for this critical section, we'll decrement the count if this read count is equal to 0. What does it mean? Can anybody put on chat? Read count is decremented, and if read count equals 0, what is meaning? So meaning of this is very simple. This is the last reader. See, this read count, if read count is equal to 1, that means only one reader is there. If read count equal to 10, that means 10 readers are there. Now, if read count is decremented, that means it was 1 and it becomes 0. That means it was the last reader. Like first reader acquires lock, last reader has to read the lock, RW mutex. So this will be released so that if other writers are there, they will be allowed to write the data. Okay, and signal mutex, because we want to safeguard it with wait and signal. So this is somewhat important thing where we want to allow multiple readers. How we allowed multiple readers is very simple. Talking in terms of logical steps, we'll make use of one variable called as read count, which will denote how many active readers are there. Initially nobody is active, so it was initialized with 0. Okay, now if read count, every reader process will increment the read count, and first reader will acquire lock on read write mutex. Only first reader, remember. One of the problem with this approach is if so many, so definitely readers are getting the more privilege. Why? Because if already somebody is reading, other readers will be directly given access to that, and only last reader will release lock so that writers will continue writing. So definitely here the writer may result in some sort of starvation. Okay. So two variations are mentioned here. In first variation, no reader kept waiting unless writer has permission to use shared object. What is meaning of this? If no writer is writing there, reader is not supposed to wait. That is what we did in the previous solution. Second variation is once writer is ready, it performs write as soon as possible. That means we need to provide priority to writer, and there is a reason behind this. See, writer usually updates the variable. You imagine something like you are watching the score of say cricket, and updation of that score is done by the writer, and others are just readers. We are always interested in the latest score. That is the reason we need to provide priority to the writer. There is no point if you read the old score, right? So better option is whenever writer is ready, that means whenever new score is available, it perform the write operation as soon as possible. That means we need to provide priority to writer. Okay, so that could be another solution. Anyway, both the solutions will lead to the problem of starvation. Okay. And by providing some lock like reader rights, where we call as shared locks, and writing processes are called as exclusive locks. So shared locks and exclusive locks. Okay. So this is the second. Third one is again more popular problem, dining philosopher problems. Uh, have a look at this diagram. So these are the chairs. 1, 2, 3, 4, and 5 chairs are there. So this gives me 5 philosophers. So we have a processes called as a philosophers, and they spend their life doing two things: either they are thinking or they are eating. Philosophers, either they will be thinking or they will be eating. So they are performing just two things. One is thinking and eating. If they are not eating, they are thinking. Okay. If they want to eat, if they are hungry, then there is protocol for that. So for example, they don't interact with their neighbors, number one, and they occasionally try to pick up two chopsticks. Here, if you can check, this is the chopstick. This is one more chopstick. This is one more chopstick. So for 5 philosophers, there are 5 chopsticks. You imagine this like a spoon, fork and spoon, something like that. But we don't want to distinguish between fork and spoon, so that is the reason the chopstick is the thing utilize there. Okay, and we have plates there, or you call it as a bowl. So this is one bowl. This is one more bowl. This is one more bowl. One more bowl and one more bowl. So 5 bowls are there, and common plate is there in which rice is stored. So assume there's rice to eat. So overall, we have a round table with 5 philosophers, 5 plates, 5 chopsticks, and 5 bowls and 1 rice plate. Now the protocol for eating is the philosopher should pick up 2 chopsticks. Now, because this is a round table, there is 1 chopstick on left hand side and 1 chopstick on right hand side of every philosopher. Okay, and they need to acquire both chopsticks in order to eat. So picking up just one at a time. It's not like I'll pick up both at a time. No, I'll first of all pick up one and then second, something like that. Right. So now, for example, if I give some sort of number, so suppose this is philosopher number 0, this is philosopher number 1, this is philosopher number 2, philosopher number 3, and philosopher number 4. Similarly, I can give numbers for chopsticks also. So something like this is 0, this is 1, this is 2, this is 3, this is 4. Okay. Now you can formulate something like for ith philosopher. For ith philosopher, what I need is chopstick on left hand side, on right hand side. Now talking in terms of numbers, maybe I need chopstick I plus mod 5. Why mod 5? Because it is you looking at this diagram, you can see that it's like a circular cube. So for example, for philosopher number 0, what I need is chopstick 0 and 4. For 4, I need 3 and 4. For 3, I need 2 and 3. For 2, I need 1 and 2. For 1, I need 0 and 1. In all, I can say for ith philosopher, I need I plus 1 mod 5. Something like that. Okay. Now, in order to provide solution for this, for example, data set is a bowl of rice, and now we have 5 semaphores, and all these 5 are initialized with 1. That means each semaphore safeguard the chopstick. Because there are 5 chopsticks, we need to have 5 semaphores, and then these are like chopstick of 5. Now for this, because 5 philosophers are there, chopstick of 5 is there. Now the code for, or rather pseudocode for ith philosopher is given there. This is very simple thing. Get the ith chopstick, try to get I plus 1 mod 5th chopstick. If both are available, you can perform it. Once you finish eating, leave the chopstick, ith chopstick, and leave next. Maybe on left hand side and maybe on right hand side. So meaning of this is very simple. Try to acquire lock on chopstick. Once you got it, do eating. Once you're done eating, release both the chopsticks. And once you're done eating, now you are thinking. Something like this. And this is happening in infinite loop. Do you know what the problem with this? So for example, every ith philosopher tries to pick up ith chopstick. Now going back here, for example, suppose it started with 0 and it has picked 0 chopstick. That is the first weight is satisfied. Now suppose time quantum of this process is finished and now it is turned off first. It will pick up first chopstick, second will pick up second chopstick, third philosopher will pick up third chopstick, fourth philosopher will pick up fourth chopstick. Now at the end of this one loop, what happened is every philosopher has one chopstick in their hand and they are waiting for next. Everybody is waiting, kind of circular wait. This situation is like deadlock. This situation is deadlock. So whatever the solution is there, even though logically it is correct, this will result in deadlock. Okay, so that creates a problem. That creates a problem. Okay. Now, what is solution in order to handle the deadlock? 2-3 solutions are mentioned here. Number one, allow at most 4 philosophers. So if that round table has 5 seats, we'll just allow 4. So that will make sure. So this could be one of the possible solutions. or allow the philosopher to pick up fork only if both are available. So that means whenever I want to pick up the chopstick, that has to be done in the critical section. So picking up chopstick, if both are available, then I'll pick up left and on right hand. Otherwise, I'll simply release it. Or second one is use an asymmetric solution in which odd numbered philosopher pick up first the left chopstick and then right chopstick, and even numbered philosopher will pick up first right chopstick and then left chopstick. So in all three way we can remove the deadlock. Okay, so that is the solution with dining philosopher. Now next part is the monitors, but now monitor will see in tomorrow's lecture. Right now I just want to share one more thing with you, and that is just a minute, let me check. I logged in there. Okay, let me share it. Share the browser. Okay, fine. One important thing is today you are supposed to give ISC one quiz. Okay, separate kind of. I really don't know whether you've gone through this kind of question. So some sort of calculated questions are there, and MCQ is there, and also drag and drop kind of questions are there. So I just want to show you how to deal with drag and drop kind of question. Before that, is it visible? Moodle course operating system, is it visible? Please put on chat. Okay, fine. So what I'll do is I'll go to the question. Okay, no problem. I'll just show you one thing. I'll go to the questions part and I'll just show you, for example, say boot process, for example. I'll just preview this question. So for example, this steps of system process. So these are the steps actually, and you are supposed to simply drag and drop in whatever the things are given there, something like this. Okay, so this kind of question will be there. So for example, if I start again, let me close it. So this is this kind of question, drag and drop, where options will be available to you. Right now this ISC quiz is hidden from student. I'll open it at 4:30, I guess. I just want to ask you the question like, do you have any scheduled quiz today at 4 or 4:30? Or even before that also, if you have. DB is there at 4. Okay, 4:30, it is 4:30. Because my quiz will be just for 15 minutes. 13 questions are there, 1, 3, 13, and 15 marks are there. So I'll just give 15 minutes for that. So let me know the time. So I'll open the quiz for that time only. And remember, the quiz you will attempt, only one attempt will be allowed, and that will be count for ISC 1. What is the question? If we do that, will be an issue. No issue. The quiz will be on mobile. So if you have what I can say, touchscreen mobile, you can drag and drop, no problem. Okay. On mobile, so you can drag and drop. Even that is more easy. No issues at all. Just I wanted to know time from your side. 4:30, okay? 5 p.m. absolutely no problem. Or even at 3, 3:30. Just give me any suitable time. 5 p.m. Okay, fine. So we have finalized. Okay, 3 or 4, no, but at 4 you have already DB it is no. Okay. Fine. So everybody is saying 5. So I'll schedule it at 5. Okay. So let me stop sharing this. So today at 5 p.m. there will be ISC 1 component quiz. Okay. So let us stop here.